Welcome student, Atropine Alkaloid. We are going to discuss in today's lecture. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous Ahmedabad. Let's begin with the introduction. As you know, the atropine is an alkaloid. It is found in a deadly nightshade Atropa belladonna L and thorn apple, that is Datura stramonium L, along with an optical active alkaloid, that is hyoscyamine. Well, heating hyoscyamine in ethanolic alkaline solution yields hyoscyamine and dextroliboratory, which was found identical with atropine. So this is the structure which is identical with atropine. Now you might be puzzled why I put these two GIF over here. They are going to show you this pupil open up and close. This is either we can say structure which is modified structure, and this is actual one. And it is for what? Then we need to study this one. It is extensively used in ophthalmology to dilate pupil of eye. So this is a dilation of pupil of eye that is animated, and this is the real picture. You can see here the pupil will open up and close, and for that this atropine is extensively used. It deactivates salivary and gastric glands. Atropine is a crystalline compound having melting point 118 degrees centigrade with a beta test. Molecular formula would be C17H23NO3. It gets hydrolyzed when warmed with a solution of barium hydroxide to give a racemic acid, that is dextro and levorotatory compound, that is tropic acid, and an optically inactive alcohol called tropine. So we need to study these two compound to study the atropine, tropic acid and tropine. So in this lecture we're going to include the structural information of tropic acid and tropine, and then both of these will going to form atropine. So that is the things that we need to include in this lecture. Atropine is generated when a mixture of this tropic acid, already I have said that this racemic mixture of tropic acid and tropine, that is non-optically active part of the atropine compound, that is tropine, and both of these when heated in the presence of hydrochloric acid will going to get atropine. Here is the reaction which already we have discussed, that this compound on hydrolysis gives atropic acid and tropine, and this tropic acid and tropine when heated in presence of HCl will going to get the compound back atropine. This reaction showed that atropine may be either an ester or an amide. An amide produces a carboxylic acid and a primary or a secondary amine on hydrolysis. But nitrogen atom in atropine was a tertiary base, confirming that atropine is a tropine ester of tropic acid, tropine or tropate. So these are the three structures, and their ester is there. That means atropine is a kind of ester made up of tropic acid, tropine and tropate. Characterization of hydrolysis product of atropine lead to confirmation of the structure of atropine. Now let's go for the structural determination of first tropic acid and then followed by tropine, and then we're going to study how both these react with each other in presence of HCl to give atropine. Well, tropic acid having molecular formula C8H10O3 consumes one equivalent of alkali to form salt, showing it to be a monobasic acid. So it is a monobasic acid. It forms monoacetate when treated with acyl chloride, confirming that the presence of hydroxyl group also there in this tropic acid compound. It undergoes dehydration when heated strongly to give an optically inactive unsaturated carboxylic acid named atropic acid, which forms benzoic acid on oxidation. The formation of benzoic acid suggests that atropic acid and tropic acid also have benzene nucleus. That means it has this aromatic nucleus. Here is the example that tropic acid, that is C8H10O3. This is the compound. On heating, it will convert it into atropic acid, and on oxidation of this atropic acid we are going to get the benzoic acid. That means there is a benzoic acid nucleus or benzene nucleus is there in this tropic acid compound. There are only two structures, structure 1 and 2. 2 is missing over here, typological mistake, that can be confirmed by atropic acid. Atropic acid was assigned structure 2 because oxidation of atropic acid yields phenyl glyoxylic acid, while structure 1 would have given benzaldehyde. Here structure 1 is there, structure 2 is there, and when we consider structure 2 of atropic acid on oxidation, it will going to give you phenyl glyoxylic acid like this one. Since atropic acid is formed by dehydration of tropic acid, the structure of tropic acid must be either structure 3 or structure 4. The structure of tropic acid was confirmed by the synthesis and it would be structure 4. Here structure 3 is there for atropic acid, structure 4 is there, but the synthesis revealed that the structure 4 is the real structure of tropic acid. Here is the synthesis of tropic acid by Mackenzie and Wood synthesis in 1919, where acetophenone treated with hydrocyanic acid or hydrogen cyanide and it is going to give adduct here, and we're going to get this adduct on hydrolysis. It gives atrolatic acid, which on heating at reduced pressure it lose one water molecule and we're going to get this atropic acid, and that atropic acid treated with HCl will gives this chloro derivative of atropic acid, and on further treated with potassium carbonate followed by treatment of acid, it will going to give us the racemic mixture of tropic acid. It must be noted that the addition of hydrochloric acid to atropic acid gave anti-Markovnikov product, and Markovnikov product would have reproduced atrolactic acid on treatment with aqueous potassium carbonate. That here you can see this atrolatic acid will converted into tropic acid. Another synthesis is Muller and Wislicenus synthesis in 1918, where ethyl phenyl acetate will treated with this ester and sodium ethoxide. It will going to gives the carboxylic ester derivative converted into aldehyde derivative, which is ketoenol form. So enol form is it going to gives this tautomerism, gives enol form, which treated with aluminum amalgam, moist ether. When it treated with aluminum amalgam and moist ether, it will going to gives this primary alcohol, and then treated with base hydrolysis followed by acid treatment, it will going to gives the racemic mixture of tropic acid. Third is the Blick ethyl synthesis 1952, where phenyl acetic acid treated with this Grignard reagent. 2 mole of this Grignard reagent will going to gives us phenolate. Phenolate on treating with this formaldehyde followed by acid treatment will gives atropic acid. For further ethyl established the configuration of one of the isomer levodotropic of tropic acid by its correlation with this alanine, and natural tropic acid may be represented as the sinister, that is levotropic acid, and this sinister levotropic acid has this structural arrangement. Tropine has a molecular formula C8H15NO, which correspond to 2 dBes. It forms a crystalline addition product, that is C8H15NOCH3 plus I minus, that is the iodide salt, with one molecular equivalent of methyl iodide, and liberates one molecule of methyl iodide when heated with hydroiodic acid at 150 degrees centigrade, showing that a tertiary nitrogen having a methyl group attached is present in the structure of tropine. The oxygen atom was present as hydroxyl group because tropine formed monoester. So after discussing tropic acid, we are going to discuss the structure of tropine having molecular formula C8H15NO, and this treatment of methyl iodide will going to give us information about the oxygen atom present is in the form of hydroxyl group because tropine from monoesters. Ledenberg in 1883 to 1887 studied the reaction of tropine and confirmed the presence of six-membered nitrogen-containing heterocyclic ring in tropine compound. Heating tropine with hydroiodic acid below 150 degrees centigrade gave tropine iodide by replacement of hydroxyl group with iodine atom, which on reduction formed dihydrotropidine, which when distilled with hydrochloric acid HCl produced noriodic hydrotropidine by removal of an methyl group. Finally, nordihydropropidine was distilled with zinc dust. Here C is their typological mistake. Zinc dust to yield 2-ethylpyridine. Here is the reaction. We have tropine treated with hydroiodic acid below 150 degrees centigrade temperature. We are going to get the iodide, and on treating with reducing agent or on doing reduction, we are going to get dihydrotropidine. That dihydrotropidine treated with HCl, on hitting with HCl, we are going to get nordihydrotropidine, and on treating it with zinc dust distillation, we are going to get 2-ethylpyridine. So this is the structure of 2-ethylpyridine. He suggested two structures for tropine largely based on his study and functional group information. The best feature of this structure was their carbon skeleton, which was similar to that of 2-ethylpyridine. But this structure failed to explain the saturated nature of tropine. It does not add on bromide. Here is the Ledenberg structure of tropine. This one, either this one. Marling in 1891 showed that the oxidation of tropine with chromium trioxide produced a carboxylic acid with the same number of carbon atom named racemic mixture of tropinic acid. He argued that the hydroxyl group must be present on the ring carbon atom and proposed two saturated structures for tropine. Here the tropine on oxidation will give tropinic acid. This is the structure for that. Marling structure for the tropine is this kind. Willstatter reinvestigated the oxidation of tropine with chromium trioxide and isolated tropinon, that is the structure C8H13NO, which behaved as a ketone, confirming the nature of hydroxyl group as a secondary hydroxyl group in this compound. Further oxidation of tropinon with a chromium trioxide produced a tropinic acid, which when oxidized with chromic acid yielded N-methyl succinamide, confirming the presence of five-membered nitrogen-containing heterocyclic ring in tropine. Nitrogen atom must be common to both piperidine as well as pyrrolidine ring, since there is only one nitrogen atom present in tropine. So tropine on oxidation will convert it into tropinon. Tropinon on further oxidation converted into the racemic mixture of tropinic acid, and it is further oxidized in presence of CrO3H2SO4, gives N-methyl succinamide, and that will going to confirm that it have a five-membered N nitrogen containing heterocyclic ring in tropine. He then studied the reaction of tropinon and prepared several derivatives of tropinon. Tropinon, when treated with nitrous acid, gave a dioxime. Similarly, reaction of tropinon with benzaldehyde gives a dibenzylidine derivative. These products confirms the presence of CH2COCH2 moiety in tropinon. Here the dibenzylidine is going to be obtained on treating with benzaldehyde and treated with HNO2, 2 mole of HNO2, tropinon is going to give you dioxime, and that sorry, that confirms the presence of CH2COCH2 group in tropinon. Based on these findings, Willstatter modified Marling structure and proposed structure for tropine, which was found correct by further degradation studies. This structure is given by Willstatter modifying Marling structure, that this is the real structure of tropine. The dehydration of tropine with sulfuric acid followed by Hofmann exhaustive methylation of the product yielded tropylidine, that is cycloheptatetraene, which confirms the presence of a seven-membered carbon ring structure in tropine. This is a seven-membered carbon ring structure in tropine. It's a bicyclic structure. So treated with H2SO4, we're going to get this. On exhaustive methylation, that is Hofmann degradation, we're going to get this seven-membered ring structure. Hofmann degradation will give tropylidine, that is a seven-membered ring structure present into tropine. The Hofmann exhaustive methylation of tropinic acid yielded an unsaturated dicarboxylic acid, that is C7H8O4, which is reduced to pimelic acid then. So this is a tropinic acid, and we performed Hofmann exhaustive methylation process, that is the treatment of methyl iodide followed by silver hydroxide. On heating, we're going to give a ring opening reaction. Dicarboxylic acid is going to be obtained. On reduction with sodium amalgam will gives pimelic acid, and we're going to get the ring opening reaction, and we can remove this nitrogen part from the tropinic acid, will gives pimelic acid. Reaction of tropine explained by Willstatter formula. This is the reaction. Treated with hydroiodic acid, we're going to get that is a tropine, conversion of this tropine to 2-ethyl pyridine, So tropine treated with hydroiodic acid will give tropine iodide. Tropine iodide on reduction gives dihydrotropidine. Dihydrotropidine treated with HCl on distillation gives non-dihydrotropidine, and that further treated with zinc dust on distillation it gives 2-ethyl pyridine. Oxidation and derivatization of tropinon. Tropi, Tropinon oxidation gives tropinon. Tropinon on further oxidation gives tropinic acid. Tropinic acid on further oxidation with chromic acid will going to gives us N-methyl succinamide. Tropinon on treated with benzaldehyde and nitric acid will gives oxime and dibenzylidine derivative respectively. Now synthesis of tropine. Structure of tropine was confirmed by several syntheses. First synthesis is Willstetter synthesis in 1903. That is the first synthesis of tropine that is reported by Willstetter starting from uh, sub Saberon, that is cycloheptanone. Saberon was converted to cycloheptatetraene in the 7 steps. Tropine was obtained in 10 steps from cycloheptatetraene. This is the reaction. So Saberon on reduction followed by treatment with hydroiodic acid will going to get this iodide derivative. Then it is treated with the potassium hydroxide, KOH, alcoholic KOH will going to gives us cycloheptene. Cycloheptene on treated with bromine will going to get dibromo derivative. Dibromo derivative treated with dimethylazide, or we can say dimethylamine will going to gives us this nitro derivative, N-methyl derivative. On exhaustive methylation it gives cycloheptadine, and that dine again treated with bromine 1,4 addition reaction is going to be obtained, will gives dibromo derivative. Treated with quinoline at 150 degrees centigrade will going to get cycloheptatetraene. uh, Cycloheptatetraene on treated with hydrobromic acid will going to get again bromo derivative. That treated with dimethylamine gives this N-methyl derivative. That is treated with sodium ethanol followed by treatment with bromine in presence of HBr gives bromo derivative, and then that is warmed with ethanol will going to gives us this uh, bromo derivative of tropine. That further reacted with potassium hydroxide will gives us this N-methyl derivative of free radical of bromide is there. That treated with potassium iodide followed by silver chloride. That means bromine is converted to iodide derivative, iodide is converted into chloro derivative, and then further heated with when further heated methyl chloride is going to be substituted and we're going to get tropidine. Tropidine treated with hydrobromic acid will going to give again bromo derivative, which is further treated with H2SO4 at 200 degrees centigrade temperature will going to get cytropine. Cytropine on oxidation will going to give us tropinon. Tropinon with zinc distillation and further treated by hydroiodic acid will going to give us tropine. So 11 steps is there for this synthesis. Now treatment of 1-dibromocycloheptane with dimethylamine result in dihydrobromine brominium and nucleic substitution. Double dihydrobromination product was not formed probably because stereochemical requirements were not met there. Uh, in that part, the synthesis of tropine given by Sinister. Second point, addition of hydrobromic acid to cycloheptatetrine yielded symmetrical bromo uh, derivative through more stable carbocation reaction. Here you can see that more stable carbocation is going to be obtained. Carbocation 2 is not stabilized by resonance because it is not a planar structure, and carbocation 1 is more stable because it is attached to sp3 carbon atom, while structure 1 is attached to sp3 and sp2 carbon atom, and sp2 carbon atom is more electronegative. So, addition of HBr in presence of acetic acid to tropidine gave symmetrical bromoderivative through more stable carbocation. Here you can see the reaction is given. Uh, Robinson synthesis 1917. This is the Robinson synthesis. Robinson designed a beautiful synthesis of tropine in a single step reaction. Uh, though the yield was poor initially, tropinon was obtained in 81% yield in one step after few modifications. Retrosynthetic analysis of tropine led him to believe that tropine skeleton could be constructed from a simple compound in a single step, and that is the application of retrosynthesis. You need to go in a reverse logic. First target molecule is considered, and in target molecule this wiggly line or dotted line will going to put for disconnection. This inclined arrow suggests that after the disconnection of this molecule, we're going to get these three simple fragment, that is a synthetic equivalent, and using this three fragment we can get this molecule in a single step reaction. So this is a retrosynthetic analysis of this tropinon, gives this dione and then and methylamine and this ketone, and treatment of these three will going to gives us this target molecule, that is tropine in one single step. When a mixture of succinic dialdehyde, methylamine, and acetone was allowed to stand in a water for 30 minutes, propanol was obtained. Very simple single step reaction is going to be obtained over here. This is the reaction mechanism. Succin dialdehyde will going to treat it with methylamine. Methylamine which contain the nitrogen will going to attach over here, substituting one aldehyde group, we're going to get this one. So the pi electron will shifted on this nitrogen, and then again it's treated with this uh, aldehyde group. We're going to get this derivative where the free unpaired electron of nitrogen is going to donated to this double bond, where the pi electron shifted on oxygen will going to gives us this dialkene, which on cyclization will going to gives us tropinon. Tropinon treated with zinc dust followed by hydroiodic acid will going to gives us tropine. The yield was improved to 40% by replacing acetone with calcium acetone dicarboxylate or ethyl acetone dicarboxylate, and then it reached to 85%. The presence of dicarboxylate group at a carbon alpha carbon atom make enolic form more stable, resulting in a better yield, that is 85%. So we are going to take this instead of ketone acetone, we will going to get this derivative. uh, the product yield is increased from 40% to 85%. The yield was further improved to 81% by generating succin dialdehyde in C2 form from 2,5-dimethoxy tetrahydrofuran under acidic condition and using acetone dicarboxylic acid. So this is further treatment that 40% yield can be increased to 81% by doing this another treatment as well, where 2,5-dimethoxy methoxy tetrahydrofuran on treatment with acid will gives this aldehyde. That dialdehyde treated with methylamine in presence of HCl, and this ester will going to give us tropinon, and tropinon on treated with zinc dust and HI will give stropine, and 81% yield is going to be obtained by this way. Preparation of atropine. This is the last step. Atropine is prepared by heating a mixture of racemic mixture of tropic acid plus minus, you need to understand here. It is a typological mistake, plus or minus tropic acid and tropine in presence of hydrochloric acid, as stated earlier, we're going to get tropine. So tropine is going to be obtained, tropine and tropic acid in presence of HCl, we're going to get this atropine. This is the structure of atropine. Well, this is enough from my end. Thank you very much for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge.